Good afternoon. This is Schweitzer. Our first atomic bonding pre-learning information for advanced placement chemistry. You will have a, I would say, sort of brief pre-test for this chapter. And here's some just general information. This is using the objectives from honors chemistry and kind of just walking through them. Now again, this is a atomic bonding and structure, atomic structure and bonding. So 2 chapters from honors chemistry. So we're squeezing them down to 1 for AP chemistry, but the content is about 90% the same. So that being said, there's a lot of maybe relearning that needs to be done, but most of the content is going to be the same. We have one of our first chapters in AP Chemistry. So how does this work for content-wise? Just because you understand the content does not necessarily mean you're going to be up to date for answering some of these questions. Now, again, also in honors chemistry, we have loaded full of AP questions all over the place. So again, you could be very familiar with some of these types of questions. But as far as bonding and multiple choice, it's my experience that the majority of the atomic structure is going to be in a multiple choice form. And then in bonding, you will see that you will have maybe an equal mix of maybe some we call free response and the multiple choice. So we'll get more and more into this. Obviously, one of our main goals is to do well on this AP exam. All right. So here I have a bunch of just questions here, and we will be just kind of walking through some of these things. I will be hopefully highlighting some things that are more important than others. You are free to take notes on this particular content, and you can then use those notes on your pre-test. So make sure you're aware of that. But let's kind of go through this thing here, just sort of step in and out, maybe highlight, because there'll be, obviously, I'm not looking for you to be 100% fluent on everything for these chapters, but I would hoping to expect for some baseline knowledge, some big ideas that you had from previous years, that you at least have this baseline. Okay, how does an atom acquire mass? Okay, well, so this is a pretty important question, but let's back up a second and say, okay, well, there are subatomic particles, and there are 3 of them. We have protons, we have neutrons, and we have electrons. Protons have a mass of 1 AMU. This is what's called an atomic mass unit. You can convert that into pounds or kilograms, but it's based off of essentially a carbon atom, and it's a relative unit. Either way, it has a charge of +1 unit of charge. Neutron, again, 1 AMU. It's actually slightly bigger than this. If you were to take a proton and an electron, squeeze them together, you get a neutron. But as you see, electrons have essentially 0 mass. Okay, the neutrons have no charge, and electrons have a -1 charge. Okay, so we have 3 subatomic particles. How does an atom acquire mass? Well, in that case, we're dealing with the protons and the neutrons. I'll just symbolize it with a P and an N. This is what's going to determine an atom's mass. So a few things you might want to note about these protons and neutrons is a proton, let's say for example oxygen has 8 protons. This is very critical in the sense that that determines the element. Okay? Any atom that has 8 protons is going to be oxygen. Alright, so the neutrons, these are often referred to sort of like the glue that holds together these protons. Now keep in mind, both of these guys are located in the nucleus, very small, dense core, and the protons are all squished in there. So they're positives, and based off Coulomb's law, these positives might repel each other. So we have these little neutrons in here that sort of help it glue it together in some sense. So only way for an atom to acquire mass is to either have more or less protons and neutrons. Changing the neutrons will not change the identity of the element, but will change the mass. Changing the protons, which is not very easy, to change anything in this nucleus, requires a nuclear reaction. These are not things that happen on a daily basis around our lives. Let's keep that in mind. Nuclear fission, nuclear fusion, nuclear decay. This is what we're talking about here. So not really that much in the scope of this class. So changing the identity of the nucleus is difficult and is not something that we do lightly here in chemistry. Now the electrons, those come and go quite easily. And that is where our next question is how does an atom acquire charge? Okay, so charged atoms are going to be the protons and the electrons. We wouldn't necessarily care about the neutrons in this case. Now, like I said, protons are in the nucleus. So this is very hard to change. So that being said, to acquire charge, this might be something that is most easily done with the electrons. Electrons can be gained or they can be lost very easily. You can rub your feet along the carpet and you can pick up a charge and you can touch someone and they can snap them with electricity. We learned that as a little kid. So if you want to gain electrons, there's a fancy term for this, is called reduction. And the term for that is gain electrons reduced, GER. And to lose electrons, this is called oxidation. So it happens enough that they give it its own special term, and that is LEO. Lose electrons, oxidize. So Leo the lion says GER. Something that, because reduction and oxidation the names don't match the process anymore, we have these little acronyms to help us out. Okay, so for something to become positive, okay, that means it's going to be called a cation, and therefore it means it has a greater amount of positives than negatives, or a greater number of protons than electrons. So in this case, because the protons are so hard to kick out and bring in, we would say that the protons are, unless you do a nuclear reaction, they're kind of static. So they will not be changing. So in some sense, to become a cation, I could lose electrons, and therefore my electrons drop below my protons, and I am therefore going to be a cation. Conversely, if I were to gain electrons, I would therefore have more electrons than protons, and I would therefore have undergone reduction, and I would be an anion. So we just simply have a swapping of protons and I should say electrons. Electrons are on the outside, and in this case we call this electron cloud area out here. Electrons easily coming and going, but protons and neutrons not so much. Okay, what is the electronic structure of an atom? So in honors chemistry, we learn about electron configurations and orbital diagrams. This is something that in AP chemistry, they're never going to directly ask you to write an electron configuration. They'll ask questions sort of around it. So I'm not going to go through this, and we'll have some examples in class where you'll be able to brush up on how to do this. But essentially, if you have, let's say, for example, oxygen. Oxygen is a 1s2, 2s2, 2p, and then it'd be 4. This is the electron configuration. Now, if we had oxide, where it gained 2 electrons, then it'd be 1s2, 2s2, 2p6. Note that this is a full electron shell. Again, don't let this scare you right off the bat. We'll be doing some in class, but just trying to remind you of things we did in previous years. So this is the electron configuration, and then we have the orbital diagram. And it is going to be oxygen, 1s2, 2s2, 2p4, and below here I show the orbitals. S's have 1 orbital and P's have 3. And then each arrow represents an electron. They have opposite spins, opposite spin, and we call this thing filling separately first. We call that Hund's rule. They fill separately first, but since I have 4 of them, I need 1 more, and they're all equivalent, so I can put it anywhere, but I have the opposite spin. Okay, and then this guy would be the same thing, except this guy would just be full, and they all would be spin paired, which means they're opposite spins. Okay, periodic trends. Now, as far as trends are concerned, this is probably the big kahuna, you might say, as far as bringing all these concepts together. And let's take a few moments and just kind of, I'm going to use this area right here, and I'm just going to summarize. There's a lot of things here. You can take a look at this and stuff, but essentially I want to review 1 or 2 things. What happens when we gain a proton? What happens when we lose, or so it says it could be gain or lose for either of these. Gain or lose an electron. What happens if we gain or lose a proton and an electron? Now, all of this that we talk about here is going to be based off of the main concept, which is Coulomb's law. Coulomb's law basically states that positives and negatives attract, and that positives and positives repel each other, and that negatives and negatives repel each other. The formula, which we almost never really, we don't actually calculate anything with it, is the force of attraction between a positive charge, let's say, and another charge, could be negative, that'd be attractive force, is equivalent to the distance squared between them. There is an equalizing constant here that just makes it mathematically work. But again, we won't be calculating it, so it doesn't matter. Alright, so in this case, if I were to add protons, then I am just going to be increasing the charge. And you can think of it mathematically. This is a numerator, so increasing, so we'll say gaining the proton will cause an increase in attraction, because there's more positive and there's more the same negative, so it increases attraction. You will note that in the sense of this here, we have a nucleus here, and we have electrons going around the outside. This is a positive right here, and we're clumping all the positives together. So whenever we add a proton, we're causing this basically, this whole thing here represents the nucleus. But since electrons are spread out, this guy only represents a single electron. So we're saying sort of looking at with the focus of saying, okay, what's the attraction between this nucleus and this electron? And in this case, we also have an attraction between, let's say, these two guys as well, these two negatives. So we're having an attraction here, and we're having a repulsion here. Attraction right here, and we have a repulsion between the two guys. We also know that they're sort of landing in an energy level. So we have a couple options here. If I gain an electron, okay, what does it mean? So if I gain, well, these two negatives are going to repel each other slightly. And that's important to note, that adding another negative in here is going to repel these guys away from each other and cause it to swell ever so slightly. So gaining an electron will cause a slight increase. And that's only due to repelling other electrons. But there's a possibility that if I have to, if this energy level is full, I gotta open a whole new one, then in this case I might have a drastic increase. So if we open a new shell, then we could have a big increase in size. Same thing here goes, okay, for gaining, losing both of these guys. In this case, because I have an increase in the nucleus and electrons here, in this case, adding protons is going to increase the attraction between the nucleus and the electrons, and therefore it's going to get smaller. So if I gain, I'm going to get slightly smaller, okay? Unless, of course, I open a new shell. If I open a new shell, then it gets much larger. So this is just a general overview, and we will be talking about this in much greater detail in class, just trying to reopen some of the ideas here. How is the periodic table structured? So we'll just kind of look at this a little bit, just so we're aware. We have, the periodic table kind of looks like this. We have families. Up and down columns are called families. And then we have this sort of stair-stepping here. It's very important, basic knowledge. This side here are metals. And we have non-metals. The families tend to have similar properties, mostly due to the fact that they have the same number of valence electrons. Valence electrons are the most common thing that controls their properties. One valence electron, two valence electron. These guys vary as far as electrons concerned. And then there's 3, 4, 5, 6, 7, and then last guy is 8. These guys on the edge here have properties of both metals and non-metals. We call them metalloids. An example might be silicon. Metals tend to be very conductive, so they conduct electricity. Non-metals are non-conductive, generally speaking. So metalloids might do, in some situations, might do conductive and may not be. In the example, this is silicon, which is what we make microchips out of. All right. In which ways do atoms bond? Okay, so we have ionic, metallic, and we have covalent. A couple things about this, and we'll talk a little bit about them before. These are old. We may do a little bit of this, not much. We'll probably tackle a little bit of this on at the very end of the year. Just to kind of, there's a little video online that I have tagged if you want to, but otherwise, I'm not sure we'll do too much of that until the very end of the year, just to sort of throw a few things in there, try and catch a few questions here if we can. How do ionic bonds form? Okay, so keep in mind, ionic bonds, very important, basic thing here, is a cation bound to an anion. And there might be a lot of them. It might be a whole bunch of anions and cations. And this is just simply an attraction right here between something that happens to be positive and something that happens to be negative. And again, that's all determined by Coulomb's law. So generally speaking, lots of times this cation can be a metal, and the anion is sometimes a non-metal. So for example, we have NaCl. This is my cation, this is my anion. Of course, we call this sodium chloride. This is referring to a non-molecular substance. It is a bulk crystal. It is a huge pile of cations and anions. I could draw on that better to begin with. And it's just a big pile. NaCl is the simplest ratio of atoms. It's just saying that there essentially in this big pile is a 1 cation for every 1 anion, a 1-to-1 ratio. We call that the empirical formula. We don't say Na2Cl2. This would be really odd if you think about it, because you're sort of insinuating that there are 2 sodiums and 2 chlorines kind of clumped together in a special package, maybe like a molecule, which it's not. Bulk crystal, very important property of ionic compounds. Again, we have things that might say, okay, not to get too much into it, but ionic radiuses and melting points of ionic compounds. So a lot of this has to do with Coulomb's law, and we'll talk more about that. We have a basic idea that if you have a cation and you have an anion, and you look at Coulomb's law, the force equals the charge of the cation, charge of the anion divided by the distance squared. Then the bigger the charges you have here, then the more it's going to attract, and therefore melting points go up. Keep in mind, to melt this thing, you literally have to break this crystal apart. When you heat it, you cause these particles to shimmy back and forth, and then eventually these snap, these attractions, and they fall apart and melt. So increasing the charges increases the force, which increases the melting points. Conversely, if I want, size also matters in this case, although not as much, but if you were to reduce the size, then they get closer together, and then this guy's protons, electrons around the outside, is a little bit closer to this guy's electrons. So this spatial difference is smaller. So smaller size means greater force, just mathematically, which means bigger melting points. All right. How do covalent bonds form? A couple things you might note about this is that, generally speaking, we're looking at a nonmetal bound to a nonmetal, and it forms a molecule. Can't stress that enough. So H2O is an example of a molecule. Okay. We have electrons that are sharing. This is a single bond. So molecules have singles, doubles, and triple bonds. Do ion compounds have singles, doubles, and triples? Absolutely not. They're not sharing electrons. The electrons get transferred from one ion to the next. So this guy is a cation because it lost an electron to the anion. All right. So in this case, we're sharing electrons, and we form a molecule. We can draw Lewis dot structures of these things. Again, very occasionally they'll have you draw a Lewis dot structure, but there's some things about these molecules that we might want to be able to ascertain. Some properties of these things. Again, we're looking at why one molecule might stick to another molecule. That stickiness or attraction would determine its melting point. Okay, so why would one thing stick? Well, again, the only reason why we have attraction in chemistry is Coulomb's law. force equals a charge of one thing times a charge of another thing over distance squared. So apparently, if two things are going to stick together, they must at some point have a negative area and a positive area. Now, it might not be that big. No, ionic compounds have massively large full charges, full positive one, full negative one. These guys don't get this full charge. It gets what we call a partial charge. We draw this little thing here. It looks like that. It's actually the lowercase symbol of delta, or to relate to the it means delta, and it would be, you would say this like that. -1 means partial negative charge, not meaning full positive, not full negative. But if this is negative, then this side must be partial positive. And this is partial positive, this is partial negative. So the forces of attraction are much smaller. But if you get a lot of them, they can build up. And this idea of here is basically how all of our neurons function, it's called an intermolecular force. It is the basis of which I would say the majority of our body works. Why do your lipid bilayers stick together? Why things transfer between cells? It's just pretty much all intermolecular forces. Inside this, we still have our covalent bond inside that molecule. And of course, this is the covalent bond is an intramolecular force and has nothing to do with the melting point at this point. Either way, so we call something that's got a little partial negative, partial positive, a dipole. And you can have a big dipole or a small dipole. Another name for that is dipole moment, which is kind of a number. And if something has a dipole moment of 0, then it would have absolutely no dipole. All right. Types of solids. Okay. We have ionic. We have covalent. And we have metallic. And we have what's called, another version of this is called network covalent. Essentially, network covalent is like an ionic compound, forms a bulk crystal where everything is attracted to everything else. It's in a big pile. This thing also has a bulk crystal, which only works really with like the carbon family, carbon, germanium, and silicon. Otherwise, these are some types of solids. Ionic compounds are always solid. Network covalent, always solid. Metals are usually solid at room temperature, but we have some exceptions like mercury. Covalent, on the other hand, can be solid, liquid, or gas, being on the intermolecular forces. Alright, so looks like we're winding down here. What is the difference between formulas and percent mass of a substance? Okay, just a quick little heads up here. We have, for example, H2O. Alright, so this thing, but by the formula is saying that we have hydrogen present and oxygen present in a 2-to-1 ratio. So there are 3 particles total. 2/3 of them are hydrogen and 1/3 of them are oxygen. But because the hydrogen atom has only 1 proton and generally doesn't even have any neutrons, it has a atomic mass, or we might think of it as being a mass number of that atom, or mass of being 1 AMU. And there's 2 of them in there. There's 2 of the 3 of that. So of that we have 2 of them, 1 AMU. So that's my 2 hydrogens. Okay, and then we have oxygen. Now the oxygen, granted there's only 1 of them there, so only 1/3 of them are actually oxygen. But oxygen has 8 protons, and on average, because neutrons can vary, 8 neutrons, for a grand total of 16 AMUs. So now, even though I have a 1/3 of my total particles are oxygen, 2/3 of my total particles are hydrogen, I can't really say that 2/3 of my mass is due to hydrogen. In this fact, the total mass of this thing, hydrogen is giving me 2 AMUs, and the oxygen is giving me 16 AMUs. So the whole thing weighs 18 AMUs. 2/18 is going to be the hydrogen, and 16/18 is going to be the oxygen. So percent by mass is pretty important. Because it's always locked in this ratio, my percent by mass will always be the same. 2/18, again, I don't have a calculator present with me right now. You can divide it out times 100, but it's a small amount, is for the hydrogen, and then 16/18, or pretty close to almost all of it, is due to the oxygen. Don't forget it times 100 to get it out of a hypothetical 100. And so I have a very large percent mass oxygen and a very small percent mass hydrogen, even though I have more hydrogens than I do oxygens. So something to think about. I'm not going to talk about why something becomes polar, but essentially we have some things we already talked about here. We have our molecule, and as these things gain partial negatives and partial positives, the amount of attraction increases. And we are going to learn about why it might happen and how. And that is the atomic structure and bonding. So some things to think about.